In this section, our focus will be on alternating series, so series that have terms that alternate between negative and positive or positive and negative. The test that we mainly use to check to see if an alternating series converges or diverges is this alternating series test. Keep in mind that this test is only for alternating series. It does not apply to series that are not alternating. In our alternating series test, we check convergence by looking at two conditions. So an alternating series converges provided that 1, the terms of the series are non-increasing in magnitude. So typically when we talk about the terms, we mean the whole expression. So these would give us our terms. The reason why we're using non-increasing in magnitude, going back to vectors, remember magnitude is the absolute value. So if we're just looking at the absolute value of the terms, that means the only thing that we're really looking at is this a sub k. We're going to ignore the -1. So if you ignore the -1 that alternates between negative +1, and you look at the terms, as long as those terms are positive, so greater than 0, and as you go up in your k values, the terms are non-increasing, so they do not increase for some value n, then you've met the first condition. The second condition just states that if the limit, and here we're ignoring the -1 and we're just looking at the a sub k, if the limit is equal to 0. So if both of those two conditions are met, then our alternating series converges. Now we're adding another test. So we have to really be careful with all the tests that we keep adding, that they're appropriate for the series. In an alternating series, we cannot use the integral test. And the reason why is the integral test specifically states that the series has to be positive. And alternating series, the terms are not always positive. In fact, half the terms are negative. However, we can use divergence test. So if you take the limit and it's not equal to 0, then you can conclude that the series diverges. So oftentimes when I use the alternating series test, I actually do the limit first, because if it's not equal to 0, then I can conclude that my alternating series diverges. And then I'll actually check number 1 second. So this is what I mean. I have this alternating series. Notice that my a sub k is natural log of k over k. So something that you should note is that going back to our alternating series test, notice that it's to the k plus 1. That actually doesn't matter. Whether it's to the k plus 1 or the k doesn't matter. And in fact, you could use k plus 1, k minus 1, 2k plus 1. It doesn't matter what that k value is defined as. The point is that we alternate between positive, negative, or negative, positive. So my a sub k is natural log of k over k. I'm going to check the second condition first. I'm going to look at part 2 and take the limit as k goes to infinity of natural log of k over k, which is infinity over infinity. I'm going to go ahead and use L'Hopital's and take the limit again as k goes to infinity, and I will get 1 over k over 1, or simply 1 over k. Now I know that that limit as k goes to infinity is 0. So I've met the first condition, or the second condition actually, of the alternating series test. Now I'm going to go back and check the first condition. Is it non-increasing? That's not clear. I'm looking at natural log of k over k. Remember, we're ignoring the -1 because we just care about the magnitude. And my k value starts at 1. If I put in 1 for k, I have 0 over 1, so it's 0. If I put in 2, I have natural log of 2 over 2. I don't know what that is. So oftentimes, what we'll do is we'll go back to calculus. I'm going to define this function, natural log of x over x. And in calculus, if the derivative is negative, the function is decreasing. So that's all we have to do, is compute the derivative. Again, the only reason why I'm doing this is because it's not clear whether this is non-increasing in magnitude. When I compute the derivative using the quotient rule, I get 1 minus natural log of x over x squared. So when is this derivative negative? Well, the x squared is always positive or 0. So really all I care about is the numerator. I'm looking at where this is negative because I'll have negative over positive and the derivative will be negative. So 1 minus natural log of x is less than 0, losing my voice, as long as the natural log of x is greater than 1. So the natural log of x is greater than 1 when x is greater than e. And you can go ahead and graph the natural log function to verify this. Remember, natural log at 1, it's at 0, and at e, it's at 1. It does that. So for values, x values greater than e, natural log of x is greater than 1, so 1 minus a number that's greater than 1 is going to be negative. So I can conclude that as long as x is greater than e, my derivative will be negative. So as long as x is greater than e, e is approximately 2.7. So as long as x is greater than 3, right, we're looking for some n value that's an integer. So if x is greater than 3, then our derivative is negative. That was a lot of work, which is why I usually take the limit first, because I don't want to talk about whether it's non-increasing if I don't have to. So all this shows is that our a sub k is non-increasing for k values greater than 3, which means that we met condition 1. We found some n value where our series is non-increasing. So then we can conclude that the series converges by our alternating series test. In example B, we have an alternating series, 3k plus 1 over k, and then we have our -1 to the k plus 1. So it is alternating. Again, I'm going to do my limit first. I'm going to take the limit as k goes to infinity of 3k plus 1 over k. That's going to be infinity over infinity. instead of doing L'Hopital's, I'm just going to rewrite this as 3 plus 1 over k. So I could see that as k goes to infinity, 1 over k goes to 0. So my limit is equal to 3. And I'm done. So diverges by, and I'm not using the alternating series test here. This diverges by the divergence test. Another example. So I have an alternating series. This looks very simple, right? It's just 1 over k, which we saw that that was a special P series called a harmonic series. I'm going to use the limit first as k goes to infinity of 1 over k. That's equal to 0. So it's met the second condition that the limit is 0. So let's talk about non-increasing. I'm actually not going to take the derivative. The reason why I took the derivative on the first example was because it was natural log of x over x. It wasn't clear if it was non-increasing. But when you look at 1 over k, and here we're starting with k is equal to 1. So the terms would be 1, 1/2, 1/3, 1/4, and so on. This is clearly non-increasing, and I don't have to do any algebra. I can just state that it is clearly non-increasing. And that's because my numerator is constant. It's not changing. The only thing changing is my denominator. So this alternating series converges by our alternating series test. However, recall that if the negative were not there, if we're looking at the series 1 over k, that's a harmonic series, and that actually diverges. So notice that the alternating harmonic series actually converges, whereas our harmonic series 1 over k actually diverges. And the reason why is that sometimes when you look at alternating series, remember you're adding and subtracting numbers. So because of all that subtraction, you're reducing your sum. So you could have a series non-alternating that diverges, such as the harmonic series. And once you make it alternating, it actually does converge. The next thing we want to talk about is the remainder in an alternating series. This theorem we're going to look at only works for alternating series, and that's really important. So let's just assume we have a convergent alternating series. Then for the first n terms, the remainder is going to be defined as the difference between s minus s sub n. So here the s is the exact value of the series. The s sub n is an approximation of our series when we add the first n terms. So if you look at the difference between the exact minus the approximation, you're going to get a remainder, which is just the difference between them. If you look at the absolute value of the remainder, it's the absolute value of the exact minus the approximation. So remember what that is. That's simply the error formula. And it turns out in an alternating series only that this error is going to be less than or equal to the n plus 1 term. So sometimes the vocabulary in your textbook we'll call this a sub n plus 1 term as the upper bound on the error. So if you're asked to find the upper bound on the error, it's the a sub n plus 1 term. Something that is important here, where you do have to look at all your different tests and your different theorems, because sometimes in the theorems it doesn't matter the k value you start with, and sometimes it does. And in this case, the k value that you start with is important. If it doesn't start with k is equal to 1, then you're going to have to make some adjustments. Let's apply this theorem in example 2. For our given series, we're going to first determine how many terms are needed to approximate the series with an error less than 10 to the negative 3. So that's asking us to find n. And then once we do find that n value, we're going to actually estimate the value of the series in the second part, part 2. To be able to use the theorem, remember the first thing I need to check is I need to check to make sure that my series, my alternating series, converges. Notice that the a sub k that I'm using is 1 over 2k plus 1. So for this alternating series, I want to first take the limit as k goes to infinity of 1 over 2k plus 1. Notice that that's 1 over infinity, which is 0. So it meets the first condition of the alternating series test. Also, it's clearly non-increasing. And in this case, I can say that without taking the derivative or doing anything special, because if put in k is equal to 1, I have 1 over 3. If k is equal to 2, and I'm just looking at the a sub k, right, the magnitude, ignoring the negative. If k is equal to 2, I have 1 over 5. If k is equal to 3, I have 1 over 7, and so on. So I can see that this is clearly non-increasing. Again, that's because the numerator is constant. The only thing changing is the denominator. So since it's clearly non-increasing, and the limit is equal to 0, then I know that I have a convergent series. Okay, and it converges by the alternating series test. Okay, so we do have a convergent series. The next thing I want to do is figure out my n value. So something to note is that r sub n, our error, is less than or equal to a sub n plus 1. And what we want to do is we want to make sure that that is less than 10 to the negative 3. So this is what I need to solve. Oops. This is what I need to solve for n to figure out how many terms I need to estimate my series. And that's where your starting k value is important. If you're starting with k is equal to 1, so now we're looking at part 1 in this question. If we're looking at k is equal to 1 as our starting value, then what that means is the a sub n plus 1 term is simply equal to whatever our expression is, and all we have to do is substitute n plus 1 for the k value. If you're not starting with k is equal to 1, you're going to have to make an adjustment because we're looking at the first n terms. So that has to be less than 10 to the negative 3, which would be 1 over 1,000. Solving this inequality, I get 1 over 2n plus 3 is less than 1 over 1,000. So 2n plus 3 is greater than 1,000. And then subtracting 3 and dividing by 2, I get 997. N has to be greater than 997 over 2, which is equal to 998 or 498.5. So I have this decimal. When we choose our n values, we always round up. So if I choose n equal to 499, then that would be an appropriate n value so that I can estimate my series with a certain accuracy, which brings me to the part 2. In your calculator, you're going to go from k is equal to 1 to 499, but you're putting in the original series, which would be the negative 1 to the k, 1 over 2k plus 1. When you put that in the calculator, when I put it in the calculator, I got a negative 0.215. But you can double check me on that. We'll look at another example. This example, we're starting with k is equal to 0. So we do have to keep that in mind. The first thing I want to do is note that my a sub k that I'm looking at is 1 over k factorial. Does this converge? Well, I know that the limit as k goes to infinity of 1 over k factorial. Again, notice that the numerator is constant, the denominator just keeps growing. So this is equal to 0. And then if I look at my terms, starting with k is equal to 0, 1 over 0 factorial. 0 factorial is just 1, so I have 1. When k is equal to 1, it's still 1. When k is equal to 2, it's 1 over 2 factorial, which is 1/2. When k is equal to 3, 3 factorial is 6. So this is another case where it's clearly non-increasing. So this converges by our alternating series test. Let's find our n value. Since we're starting at k is equal to 0, just note in general that any series that starts at k is equal to 0 of some a sub k, the first term is a sub 0, second term is a sub 1, third term is a sub 2, and so on. So what I'm going to do is note that since I'm starting at 0 instead of 1, my a sub n plus 1 is actually a sub n because I'm starting at 0. So I'm going to make that adjustment now when I solve for n. Instead of substituting in n plus 1, I'm just looking at n factorial less than 1 over 1,000. Okay, So that's where your starting k value makes a difference, because remember what we're trying to do. We're trying to find the number of terms. We're not trying to find the number that the series ends on in our summation. We're trying to find the number of terms. Now the problem with this inequality is I can write n factorial greater than 1,000. That's true. But then I have to stop. I don't know how to solve that. It's not like I can take the factorial root on both sides or anything weird like that. So in this particular case, this is as far as I can go. And then I just have to substitute in values for n. So if n is equal to 1, clearly that's not going to work. I have to find an n value so that n factorial is greater than 1,000. If I use 5, so this is where you're just experimenting. If I have, say, 5 factorial, 5 factorial is 120. That's not going to work. 6 factorial, that's going to give me 720. 7 factorial, that's going to give me 5,040. So that means my n is equal to 7. So we're choosing n is equal to 7. But remember, that's the number of terms. So if we start at 0, we actually end at 6 when we're estimating the value of our series. And then putting that in your calculator, you should get approximately 0.37. But another thing you could do here, instead of adjusting for that n value in the inequality, what you could do is just reindex. Notice that if we start at k is equal to 0 and we go to infinity of -1 to the k over k factorial, if I add 1 to my starting value, I subtract 1 to my k value in the expression. Remember, the exponent on the -1 doesn't matter. It could be k, k minus 1, k plus 1. So now our a sub k is simply 1 over k minus 1 factorial. So in this case, when you're looking at the a sub n plus 1 term, you can just go ahead and put in n plus 1 for the k value. But notice that that still gives us 1 over n factorial. However, if you did reindex and you kept it as a reindex, then you would get n is equal to 7. So that n value that you get in part 1 would be your ending value. So you can either adjust the n plus 1 term first. In our case, it was just n, not n plus 1. Or you could reindex your series. These should be the same value. If you put it in your calculator. Up until now, we have been talking about convergence, and we have been saying converges, 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 converges. This convergence that we've been talking about has been what we call absolute convergence. And since we say converges so often, we kind of leave off the word absolute. So when we say that a series converges, it means that it converges absolutely. This next definition applies to any series. However, we only use it for alternating series. In an alternating series, since the terms go negative, positive, or positive, negative, alternating. We can talk about an absolute convergence of the series. So if it converges absolutely. However, we can also look at what we call the conditional convergence. So this idea of converging conditionally only applies to alternating series. Series that are not alternating do not converge conditionally. We'll go ahead and look at this definition first. So let's say we have an infinite series and it converges. Now this a sub k is any series. It could be alternating, and in that case, the negative one is included in the a sub k, or it could be a series that is not alternating. So the series converges absolutely if the series of its absolute value converges. So in any series, if you take its absolute value and that converges, then the series itself converges absolutely. Otherwise, this convergent series will converge conditionally. So if you have a series that converges, but its absolute value does not converge, then it's conditional convergence. Let me illustrate what I mean. Remember our harmonic series. Oops. We're starting with k equal to 1, and we're going to infinity of 1 over k. If I add absolute values around my expression, they're the same, right? Because k is starting with 1, so whether I look at with or without absolute values, it's the same. So in this case, when it's not alternating, whether you check absolute value or without the absolute value, it's the same, which is why we don't talk about conditional convergence in series that are not alternating. However, if I look at the alternating harmonic, which would be the negative 1k plus 1 over k, that is not the same as its absolute value. When we look at the absolute value, that's actually taking away the negative that alternates. Which is why this theorem is only used for alternating series. So in an alternating series, it can converge absolutely, or it can converge conditionally, or it can diverge. However, that definition is not easy to use. What we use when we check for convergence of alternating series is if the absolute value converges, then the series converges. So if the absolute value will converge, then the series will converge. If the series diverges, then the absolute value diverges. What this is saying is check the absolute value first. If you check the absolute value of the series and it converges, you're done. The series converges, it converges absolutely. For example, example 3a, we're looking at negative 1/4 to the k power. Now this is a geometric series, but it's also an alternating series. I can rewrite this as k equal to 1 to infinity of negative 1 to the k times 1/4 to the k. If I look at the absolute value of this series, and you don't have to write this step, all that means is I'm taking away that alternating -1. And in this case, it really doesn't matter what k value we're starting with. It does when we do things like find n values, like in our remainder theorem. But determining convergence, divergence, starting k values never really matter. So this is simply 1/4 to the k power. And I know that this is a convergent geometric series. Because the 1/4 is less than 1, and that's my R value. So since the absolute value of my series converged, I can conclude that my series converges. In this particular problem, we're supposed to show whether it converges absolutely, converges conditionally, or if it diverges. So in the case where the series converges, it's always absolute convergence. So absolutely. Let's look at another example. I have this series, it's alternating, and I want to determine if this series converges absolutely, converges conditionally, or diverges. For me, it's easier to see if this series converges if I rewrite this as 1/k⁴. Because when I look at the absolute value of my series, again, you don't have to write this absolute value part. Looking at the absolute value of the series just means you're getting rid of the -1 alternating. It's simply 1/k⁴. And since the k is to the 1/2 power, this is a divergent p-series. So notice that this series, the absolute value of this series diverges, but we have to be careful. The theorem does not state that if the absolute value diverges, then the series itself diverges. In the event that the absolute value of your series diverges, that means it could still converge conditionally. So the next step would be to check to see if the series, the alternating series, converges. So if we look at the alternating series, and that was to the k, 1/, I'm going to just write k to the 1/2. Well, the limit as k goes to infinity of 1/k to the 1/2 is equal to 0. And the other condition for alternating series is it non-increasing? Well, when k is equal to 1, I'm at 1, and then I go to 1/, I think I'll put the square root back, square root of 2, square root of 3, square root of 4, and so on. So it's clearly non-increasing. So the series without the absolute value, the alternating series converges. by alternating series test. I can't spell alternating series test. So we'll put that all together. The absolute value diverged. The series itself converged. So in the case that you get diverge and converge, it's converged conditionally. So the series converges conditionally. So again, if the absolute value of the series converges, then you have absolute convergence. If the absolute value of the series diverges, then you could possibly have conditional convergence. You have to check the series itself. If the series converges, then you have conditional convergence. In the case where you get both diverge, then the series diverges. Well, let's do a few more examples. Example C, I have sine over k squared. I want to determine if this series converges or diverges. So if I look at the absolute value of the series, which would be k is equal to 1 to infinity of the absolute value of sine of k over k squared. The first thing I noticed is the k squared is never going to be negative. I don't really need the absolute values around the k squared. And this kind of goes back to our previous section when we were looking at the comparison test. Remember, I just have to determine if this series converges or diverges. So what I'm going to do in this case is I'm actually going to compare my series to a convergent p series. I'm going to look at the series k is equal to 1 to infinity of 1 over k squared, which is a convergent p series. Now I could take the limit, but I have these absolute values around sine of k. So if I'm going to try to use the comparison test. So the comparison test, I have to find a series to compare to, and then I have to determine which is the smaller and which is the larger. If we look at the absolute value of sine of k, remember sine fluctuates between -1 and 1. If I'm looking at the absolute value of sine, it has to be less than or equal to +1, right? Because of the absolute value. I don't have to put it between the -1 and the 1. If I take this inequality and I simply divide it by k squared, which is never negative, then I don't have to worry about flipping the inequality. So I've actually shown that the absolute value of sine of k over k squared is less than or equal to 1 over k squared, and 1 over k squared is a convergent p series. So I've shown that this series converges by the comparison test. So I can conclude that the series converges absolutely. We've shown that the absolute value of the series converged by the comparison test. So if the absolute value of the series converges, then the series itself converges absolutely. The last example in this section, I have a typo. This should be k squared over k squared plus 1 for this alternating series. What I first want to do is look at this series without the negative. So I'm looking at the absolute value of the series. The absolute value of this series would just be the k squared over k squared plus 1. But also notice that if I ignore the -1, then my term a sub k is k squared over k squared plus 1. I can see just by looking at this of having so much experience with series, that this alternating series will probably diverge. Because if we look at property 2 of the alternating series test and we take the limit as k goes to infinity of k squared over k squared plus 1, it's infinity over infinity, so you can do L'Hopital's, or you could simply divide all the terms by k squared to get the limit as k goes to infinity of 1 over 1 plus 1 over k squared. And that limit as k goes to infinity is just 1. So if I look at this series, the alternating series, and I don't even consider its absolute value, if I look at this whole series, it diverges by our divergence test. So I've shown that the series diverges. That means when I look at the absolute value of the series, that will diverge as well by our theorem. So in this particular case, we don't get absolute convergence, we don't get conditional convergence, we get that the series diverges. Okay, so it either diverges, converges absolutely, or converges conditionally. So this is the end of this section.